Hello everyone and welcome to our research paper study. Today we'll be analyzing the paper The Traveling Salesman Problem and its application in logistic practice. Problem definition of the paper. So the paper revolves around the traveling salesman problem, and the traveling salesman problem is one of logistic management's oldest and most common problems. It refers to a simple problem that is easy to define but difficult to solve in its most basic form. For a limited number of places to visit an order, these routes can be explicitly stated. But as the number of places visited expands, so does the total number of possible routes. There are several possibilities and practical applications of the traveling salesman model being used in logistics. Examples include the distribution of fuel to petrol pumps, distribution of various products from producers to distributors to customers, a doctor's visit to patients' homes, and so on. So what is the traveling salesman problem? Traveling salesman problems abide by a salesman and a set of cities. The salesman has to visit every one of the cities starting from a certain one and to return to the same city. The challenge of the problem is that the salesman needs to minimize the total length of the trip. There are many different algorithms to solve this problem. We'll be analyzing the dynamic programming algorithm. And so the time complexity for the dynamic programming algorithm is O of n squared into 2 raised to n. Using the dynamic programming technique to solve this problem, we employ the use of the following algorithm. Given function I of s, where we find the minimum of cost of I of j plus the given function for j to s not including j, where j belongs in s. I and j refer to various vertices and cities in the map, and s is the net set of all cities. Synopsis and abstract. The paper studied is the traveling salesman problem and its application in logistic practice. And here's the content of the paper revolved around two main ideas: how to convert real-world logistic scenarios into an equivalent traveling salesman problem. So this meant that converting many of the real-world issues in logistics, such as transportation costs, distance to be traveled, etc., into an equivalent values which could be assigned as the cost for a particular path. In essence, this means converting and formulating a traveling salesperson problem and transforming the complex real world logistics into a computable problem with a definite solution, and optimizing the solution. How to solve the given traveling salesperson problem? So the second idea that the paper focused on was the different ways in which a traveling salesman problem can be solved. For our purposes, we would be sticking to the dynamic programming approach. However, many alternate approaches, such as the ant colony optimization algorithm, the particle swarm optimization algorithm, genetic algorithms, etc., were also discovered. This is the example problem that we based on traveling salesman. So consider a newspaper agent delivers newspaper to a designated area every day in such a way that he covers all of the households in the area with the least amount of travel time. Calculate the minimum cost of such a travel path. Assume there are 4 households and the cost is given by the graph given below. So this is the code and the implementation details behind us trying to solve the problem, and this is the output. We can see that the minimum cost is 80. That means it's the minimum cost that we wanted is 80. Complexity analysis of the traveling salesman problem through the dynamic programming approach. Looking at the initialization and the bounds for the loop, we see that the total number of subproblems is of the order of n into 2 raised to n. This is the net number of subproblems. Each subproblem g of j of s is a computing problem, and it will be computing the minimum of s minus 1 numbers, each number computed in constant time. This is clearly O of n work per problem, as computing each one of the s minus 1 numbers, c of ij plus g of j into set of g of j and set of all numbers except for j, takes constant time per number. Finding the minimum of these s minus 1 numbers involves s minus 2 comparisons, and since s is less than n, this requires O of n time. Solving each subproblem will take O of n time. Therefore, when we combine these two ideas together, we can understand that time complexity of the algorithm would be O of n squared 2 raised to n. So what are the advantages and disadvantages of solving the traveling salesman problem using dynamic approach? So one of the benefits of the dynamic programming approach is that for a small number of n, that is the vertices that must be traveled to, the dynamic programming approach is very fast and efficient. And another advantage of the dynamic programming approach is that the practical restrictions on feasibility of different operations can be easily incorporated by forbidding the infeasible operations by setting their cost to infinity. This means that we can ignore these operations when computing a minimum cost sequence of operation. But the disadvantages of the dynamic programming approach are that the time and space complexity, while reduced from a factorial approach, from the naive brute force method, the dynamic programming approach still relies on a time and space complexity that is of an exponential order. And so, while small number of vertices are feasible and efficient, when using large values of n, the dynamic programming approach becomes cumbersome and infeasible. Conclusion. The traveling salesman problem is a very important part of real-world logistics. It is important to be able to quantify logistics situations into their equivalent traveling salesman problems. There are many different algorithms used to solve the traveling salesman problem. The most commonly used ones are the ACO algorithm for large number of vertices to travel and DP algorithm for smaller number of vertices to travel. Here we analyze the dynamic programming approach more in detail. It is found that the time complexity is O of n squared 2 raised to n. The dynamic programming algorithm for traveling salesman problem is given here. And finally, to conclude, while the dynamic programming approach is suitable for a small number of vertices, it is infeasible for large values. A benefit of the dynamic programming approach is that the paths which are infeasible can be overridden by assigning their cost as infinity.